Thanks, Jess, for the introduction. And yeah, it's my pleasure to present my recent work at Open Drive Lab. And today, I'm going to talk about two of my works. Which the first one is the flow Q learning, and the second one is the Q chunking work. Um, so let's get started. A little bit of motivation for this, for like my research in general. Everyone knows like exploration in reinforcement learning is pretty difficult, and in the worst case, it is because in the worst case we must reach every possible state in order to find the reward signal for some sparse reward task. And the typical framework or the learning framework that we have adopted before is this sort of like online reinforcement learning framework where we have our environment that the agent interacts with it and collect online rollout, which is added to the replay buffer, and then we kind of like update our belief of the world, and then try to reach as many states as possible and reach the novel state and do exploration in it. But as I just mentioned, in the worst case, it's very inefficient, right? So can we do something better? So most of my PhD or the recent work, I've been focusing on what I call sort of like more data-driven exploration, which is nothing but we have additional prior data that informs us more about the environment in advance. So rather than naively just doing online learning, interacting with the real world, to collect more data and learn more about the environment from scratch, we really focus on how do we leverage the private experience to actually make our exploration more informed and much more efficient. And this prior data can be in the form of human demonstrations. So you collect more task-specific data for some like other tasks that might not be directly related to your current task. But nevertheless, those data should be able to inform us how to do better at learning online efficiently. So there are obviously challenges with this data-driven exploration paradigm. And first of all, the prior data can be really, really diverse and very multimodal. So it's unclear how to actually learn from this very diverse multimodal data to do exploration, right? And the second part is that even if we learn something from it, it's unclear what is the best way to do online exploration. And I will go to each of the points in more detail. But first of all, let's focus on the first point. When the prior data is very diverse and multimodal, obviously the kind of the predominant paradigm for online reinforcement learning, which has been using Gaussian policy, is not going to be sufficient. This is where we really need expressive policies that go beyond Gaussian policy for doing learning that can maximally leverage offline data. So by expressive policy here, I just sort of just mean like a very popular one these days, diffusion policy or flow-based policy. And today, the work that I'm presenting mostly focus on the latter, which is a flow matching-based policy. By the way, if anyone has any question, feel free to jump in. I think I can take a few during the presentation, but if there are too many questions, I might just like move on because I feel like it's kind of the timeline, the time is kind of tight for my talk. But feel free to jump in and ask questions. Okay, so this talk I will talk about two work that leverage expressive policies and primarily address two questions. So the first work, flow Q learning, I'm going to address the first challenge that I just presented, which is how do we actually train expressive policy with RL? How do we actually model or leverage very diverse multimodal prior data for reinforcement learning? And the second part of my talk will focus on sort of the question on top of that. Even if we successfully learn the expressive policy with RL, how do we actually use that, or how do we use this technique that we develop to actually explore efficiently online? So let's jump to the first one. A little bit primer on flow matching or flow generated model. For those of you who are not familiar with it, it is essentially a generated model that tries to model a particular data distribution. Here I mark it as X1, which is the data set that you're trying to, or the data set distribution you're trying to model. And the way how fold matching works is that it is trying to merge a normal distribution or like a prior distribution. Here usually it's like a normal distribution, which I denote as X0. And it's trying to morph that distribution all the way from a normal distribution to your dataset distribution. So what we're showing here, this corresponds to the leftmost distribution, which is like a circle, to the rightmost distribution, which looks like a four-leaf clover. And essentially what we're trying to learn is to find the velocity field that can transform the normal or the prior distribution to this data distribution. And by velocity field, what I mean is basically it is defining an ODE, where upon solving the ODE from time 0 to time 1, it transforms the normal distribution to that data distribution. So the theory in flow matching really gives us a really convenient way to train such, optimize such a velocity field. And the objective is very, very elegant, where essentially all you need to do to optimize a velocity field is to randomly sample a data and a random noise, and you look at the difference between these 2 points. And you basically, for any point in between or as a straight line between the noise and the data, we're going to match that difference with the velocity field. So here, the data is X1. Again, the noise is X0. We're just taking the delta and then match our velocity field to that delta. And that will give us the correct, in the optimal, that will give us correct velocity field that actually recover the data distribution from the prior noise. And for actually sample from this distribution, as you probably already guessed, we just need to solve that ODE. So we start with the X0 with the prior distribution. And here, the easiest thing where people usually do is just use Euler integration, where essentially you take a fixed step, depending on the number of steps that you're going to take. Here, I just denote it as M. You can choose it to whatever you want. And each time you're just taking that step, adding the velocity field, integrating the velocity field to recover the output distribution, which in this case is X1. So yeah, so that's basically kind of like a really brief overview of how flow generated model works. And how do we actually parameterize the flow policy from that? It's simple, right? Like we can, instead of just training a velocity field that only based on the example and the time, here we just want to have a state condition flow model, where essentially this velocity field is additionally conditioned on the state vector. So one thing to kind of take away here is that effectively what flow policy doing is that it provides a deterministic map from noise to action conditioned on the state. So here, just for notation convenience, I'm gonna just write it as mu as z equals to x1, which is our output action. And it maps from the input noise to the output action, following this Euler integration, which we just saw in the last slide. So how do we actually train such policy in our RL, like in a way that can actually capture prior data, right? So as usual for TD-based RL method, we have some like the normal Bellman backup equation for those of you who are familiar with TD backup. But then these are not that important. The only thing to take away from this equation is that we want to train a critic network that tells you which action at each state, which actions are good and which actions are bad. And in a way, the way that we're training RL or training follow-up policy with RL is just to maximize such value, which indicated here, which I called it a value maximization term for policy. And the second term, where this is the magic where we can leverage behavior or the offline data is a behavior constraint where we can actually sort of by staying close to the offline data, we can get maximally the information that we have from some prior data. So this is the most general form of this policy or the policy optimization equation or the loss function in RL and offline RL. But in general, this term needs to be the practical. There are a lot of practical consideration to actually how to optimize this well, right? So in a very simple case for a lot of online RL methods, if we just have a Gaussian policy, this is actually extremely simple. The value maximization problem is extremely simple because you can basically use this very standardized reparameterization trick where you separate out the mean of the Gaussian and the noise of this Gaussian so that you just need to take an expectation over the noise while maximizing the value inside this. You basically take the expectation of the gradient and it will give you the correct optimization. And for the behavior constraint, it's also very simple. You can just take the maximum likelihood estimate of the Gaussian as well. But this thing doesn't directly translate to flow. For the behavior constraint, luckily, we can just use the flow matching loss that we just saw previously, because essentially what we're trying to do is we're trying to model the data set distribution as a generative modeling part, right? So that's like kind of like equivalent to what behavior constraint is doing. But the part that's a little bit unclear is how do we actually maximize value, right? How do we actually optimize this multi-step flow process to maximize some value function? To put this into a little bit more concrete term, we can actually go through this flow process one by one to see why this is like a complicated thing to do. So if we just take a three-step flow generated process, we're basically seeing that first we have the noise, which is x0, and we take one flow step which convert or transform this noise to a slightly less noisy distribution by adding this velocity field, the velocity or the delta that's predicted by the velocity field predictor. Right, so this is where we need to use the parameter to predict or to actually compute this value. I mean, to repeat this process for as many steps in our integration in the ODE until we finally get the end output action. And then this output action is put through the value function and then used in our loss function, right? So you might say that, okay, what if we just optimize this entire thing by just backpropagation, right? So this is actually the very simple thing that you could do. But the problem is like every time when you need to backpropagate through this entire computation graph, the computation graph actually kind of explodes when your number of steps or the flow step is very, very large. And we all know that backpropagation through time or through a recurrent type of model is usually very slow or unstable. And this is what we observe in practice as well, where we try to, if we try to do backpropagation through time, it often leads to suboptimal performance. Right. So
yes.
Is there a way that
Sorry to jump in.
Yeah.
Yeah. Can we go back to the last slide?
Yeah.
Yeah, for here. So if we want to do the backpropagation through time, do we need to do the action sampling process during the training so that we can sample intermediate actions and backpropagate the gradient through the sampling trajectory?
So okay, here the backpropagation through time is not with respect to the steps that are actually in the trajectory in the dynamics. This is the backpropagation through time in the diffusion or the flow generated model.
Generation process. Okay.
Generation process from the noise. This is only one step where you try to generate an action. Even that you need to do backpropagation through time if you want to optimize the parameter that actually generate the action in the end, right? Does that make sense to you?
Yeah, I see.
Okay.
Yeah.
So this is not like T. Yeah, sorry, it is kind of confusing, but T here is not the time step in the MDP. This T here is the time for the flow generated model.
Is something like the diffusion time step, right?
Yeah, exactly. It's basically the
Yeah.
same, very similar to diffusion time step. Although one thing that might already kind of confuse you a little bit is like usually for flow matching, 0 means like noise, 1 means the data. And I think in diffusion time step, usually it's the other way around, where like 0 is the data and like T is
Yeah, I see.
the noise. Yeah. So here, 1 is really the data or the action that we're trying to predict or generate, and 0 is the noise here. Okay, cool. So yeah, we just said that backpropagation through time can be slow and leads to unstable training, and this is where empirically we found to be kind of like suboptimal. So the big question here is like, can we actually avoid this backpropagation through time, which is not very optimal thing to do? So previously we mentioned that flow policy actually gives you a very deterministic map from noise to action, parameterized by this ODE process or the velocity field, right? So can we actually do distillation, right? So what if we just do distillation, but by distilling this multi-step flow model into a one-step model, right? So the idea is that we take a random noise Z and we simulate this ODE following this the velocity field that we train by like following the data distribution, right? And then we simply use a one-step model. So here is very important, one-step model that takes in the state and the noise that we just randomly sample, the same noise that we randomly sample that leads to the X1, which is the output of the multi-step flow model. And we basically have a loss that brings them close to each other. So if we optimize this loss to optimal, this one-step model will be exactly the same as a multi-step flow model. But obviously, there could be some capacity loss issue, as in the one-step model might be not as expressive as a multi-step flow model. But in practice, we found this to be actually not an issue. Right. So, okay, back to this one-step model. So what is nice about this one-step model? Well, the obvious nice thing about this one-step model is that now instead of needing to running this to a multi-step generation process, we just need to run it through one neural network, which is only one step, directly from the noise to the output, right? So this really allows us to simultaneously bring this flow model, one-step model, close to the multi-step flow model, which in this case will be a behavior cloning policy, while at the same time maximizing the value or the Q function, the creative value of this particular action. And none of these processes involve backpropagation through time. And all of the objectives or the training objectives are very, very stable. So in summary, what we're proposing here is simply having two policies. One policy is a behavior cloning policy that is trained with the standard flow matching objective, which you probably already seen from the previous slide, where essentially what we're doing is we're trying to match the velocity field with respect to kind of the difference between your randomly sampled noise and the data. So this flow policy is then used to supervise the one-step policy through this behavior constraint over here, through distillation, as well as the one-step policy is also simultaneously trained with value maximization. And then as you can see, there's nothing that really requires you to have backpropagation through time, which is why this is very stable in practice. We actually, and as we will see in a bit, outperform existing methods that do require backpropagation through time. Yeah. Okay. Great. So this is basically what we are doing instead of doing just backpropagation through time. And obviously, the thing that I'm not showing here is the critic objective. We're basically using the same RL or the TD backup. for the Q function. So
Yeah, I have a question. So
oh yeah,
will there
sorry.
be if we're distilling the multi-step flow policy into a one-step
Mhm.
flow policy, will there be a notable loss of expressiveness? So loss of
Yeah. So
performance?
yeah, this is a great question. We did have this is one of the questions that the reviewer actually asked during the rebuttal. And I believe we actually ran a behavior cloning ablation on how much the capacity loss happened through distillation. And our finding is that it didn't really have any capacity in the benchmark task that we consider. Probably because like the action distribution is not that very complicated most of the time. Unlike like image generation, which can require you to have really uh, expressive generative model. Like action distribution in general does not really require you to have a very expressive policy, especially on the tasks that we consider. But I could imagine there are tasks where expressivity could be an issue,
Yeah.
which could be like there is some solution going around it. And I think there are like a lot of open research question there.
Yeah, thank you.
Okay, so a little bit of results. How good is FQL or flow queue learning for offline RL? So we tested on 50 OG bench tests. OG bench is a recently proposed goal condition offline RL benchmark by actually my collaborator on this paper. And it's a really good benchmark. I think it has a lot of the task diversity, and it really tests on different aspects of the offline RL algorithms. And something that's also important is like on this benchmark, having an expressive policy is really important to really capture the diverse like offline data distribution. And compared to prior method that includes the diffusion methods and also other flow matching methods that use different way of extracting the policy, you can see on the bottom right, we directly compare with a method that actually uses backpropagation through time, and we outperform that method as well. So this is just to show that using the distillation and training the one-step policy directly with backpropagation is very effective. So the nice thing about our algorithm is that it's also compatible to this offline to online RL setting. If we just simply run offline RL algorithm continuously online with additional data or online rollout being added to the offline data. And we see that this is also quite competitive across the prior best offline to online RL methods. And one thing to note here is like everything is evaluated with update to data ratio of 1. So we just take one step and then one environment step, and then we take one gradient step and to do RL with it. And the nice thing about FQL is that it's also very fast. We don't see much slowdown compared to other methods. In fact, because we're doing distillation, the inference time of FQL is actually quite competitive or quite good compared to other methods, which basically requires you to actually run diffusion step or flow ODE steps in order to generate the action. Here we just need to run through one MLP to get the action by sampling a noise and then feeding the noise to the MLP. So this is actually quite, the FQL is actually quite fast. And I have actually used a lot in my follow-up work, the FQL, just because how fast it is and how effective it is to solving like RL tasks. Another thing that I just want to point out, since we have a little bit more time here, is that the hyperparameter of FQL, it doesn't seem to be that dependent on the flow steps as long as you have a decent number of steps. It seems that the 10 is sort of like a saturating point. You can't really get more performance gain by running more steps. Probably means like the distribution, the action distribution can be already captured by just training with TensorFlow steps. One thing that's really, really important for tuning our method is this behavior cloning coefficient. So I perhaps kind of like glance over this, but this is basically the common coefficient that balance how much you want to stay close to the offline data versus how much you want to maximize or kind of like exploit your Q function, right? Or maximize your Q function, right? So if you have this coefficient to be too low, then you're basically exploiting the Q function and you're not able to learn very well. And this is likely this is almost the only coefficient that we find FQL to be very sensitive to, which is also kind of to be expected just because of usually offline RL algorithms, you have this is the single most important coefficient to tune, like how much conservatism that you want your RL algorithm to have. Okay, in summary, FQL, we have sort of answered this question of how to train expressive policy with TD-based RL. And the one line answer is that we should just distill a multi-step behavior cloning flow policy into a one-step policy, and then we just backpropagate through this one-step policy to maximize its value. And we found it to be very empirically effective, and seems to be a very convenient and nice way to train expressive policy with RL. Okay, great. So now I've talked the first work is with Sahong and Sergey, and now we are moving on to the next work, which is the Q trunking. And for this work, I'm going to answer the question, which is how to actually leverage expressive policy to explore online. So going back to the main challenges I presented in the beginning of the talk, which involves prior data is diverse and multimodal, and exploration can be hard to do because usually the naive way leads to unstructured exploration. So we already know that first challenge can be reasonably addressed by FQL. How do we actually address the second challenge? Is there can we be more concrete about it, right? So the first question I kind of want to pose here is what makes a good exploration policy? So a common answer that people might say is that, okay, what if we just take the best policy that we have so far and add temporally independent action noises? Which this basically means that we have some policy and we want to roll it out in an environment, but because we want it to be a little bit exploratory, we add noises to it. So this is usually not very good because temporally independent action noises usually lead to very unstructured exploration, right? So if the goal is like a little bit far from whatever the state distribution that your current best policy can visit, you're not likely to really explore or find the goal or find the state that you want to really visit by chance. So what a slightly better strategy is to learn policy that can actually generate somewhat temporally coherent actions. So what do I mean by that? What I really mean is like a sequence of temporally correlated actions that can help you to traverse further in the environment or navigate in the environment much better. So visually, this sort of means we can really explore the environment, the manifold of the data, or in some way that can actually lead you further from whatever that you have already experienced or whatever state that your current best policy can visit. Right, this will give you a better chance of actually exploring some interesting states that will give you a good like reward signal, for example. So going back to these challenges, what I would like to modify a little bit of the challenge that I presented so far with this kind of like new sort of information is that actually the challenges of data-driven exploration is not only that prior data is diverse and multimodal, it's also that the prior data is diverse and often breaks the Markovian assumption in the sense that the prior data actually can contain behaviors that sort of exhibit this temporal coherent action and temporal coherency that could help us for exploration that we're not really utilizing it. And the second part for unstructured exploration, to be a little bit more precise, is really about we're not being very temporally coherent in our exploration policy. So to expand a little bit on this like Markovian point, a very simple example for non-Markovian data in our offline data collection process is basically human demonstration. If you think about all of the human data that you're collecting, humans are not very Markovian. We do have memory where when we are operating this the robot, usually we have more information than what the robot can see. Also, because of memory, we usually collect data in a way that is more temporally coherent than a typical Markovian policy. So the thing about doing Markovian approximation, which most our algorithm does, is that it can actually make kind of like make your data lose information. So you kind of like are not utilizing the non-Markovian part of your information in your data, right? So imagine for this kind of like a really toy example where you have two trajectory or the two distribution of trajectory going one way and the other distribution of trajectory going the other way. And for anywhere the crossroad part, the Markovian approximation will basically say that, oh, at the crossroad, we have a 50 or the equal chance of going either way. But in practice, the more temporally coherent way is actually always obeying where you have came, the direction that you have come from before, right? So one thing to take away from this is that if we naively just train RL with this non-Markovian data, with the Markovian assumption, we're not able to really exploit that in the data set. So
Yeah, I have a
so,
question. So,
yeah.
so is this issue related to the use of history context? It seems like recent advanced policies do not use any history context at all. So at the crossroad, the policy will hallucinate at whether it should turn left or turn right because it has no idea what the history is in the previous execution. Yeah.
Yeah, so that is a really great point. A history condition policy would definitely solve the Markovian issue, and you're definitely correct that the RL policy is usually not with the history condition, and that is why this is a big issue. The problem with the history condition policy in RL is that it's actually a really, really hard problem to solve. And I think that's why a lot of people tend to not use that because it has a lot of practical challenges. Essentially, you're blowing up your state dimension by dumping all the history into your state. And the stitching becomes a very, very difficult to do, especially for like value-based or TD-based RL.
Okay.
But yeah, it's a great question. Okay, so the question here that I'm trying to pose here is like, can we actually learn RL policies that can handle this non-Markovian prior data in a way that is not just like reducing it to a Markovian approximation, and at the same time generate temporal coherent actions for effective online exploration? Right. So the solution that you probably already kind of is already a spoiler is that we can just kind of tackle this challenge with action chunking. So for those of you who are not too familiar with action chunking is basically a technique where you treat a sequence of actions as one single macro action, and the RL algorithm is directly operating on this macro action or sequence of actions. So it does learning, or it predicts a sequence of action instead of just a single action at a time. So what does this translate to? It basically means that for any state, we're going to predict not just one action, but let's say here the action chunk size is 5. We're going to predict 5 actions for the current time step to 4 time step into the future, right? And then we're going to execute each of these actions open loop to get our state that is 5 steps into the future. And then we do the same thing again. We predict 5 actions at the same time for 5 steps into the future, 4 steps into the future, and then execute them open loop again. So the nice thing about this formulation is that it actually allows us to basically kind of like think about, okay, what are the nice action to execute in the near future without with a way to kind of like impose temporary coherency. So this is where it makes like temporally coherent actions actually very convenient. That can actually help expected exploration. And a very nice side benefit that we found in this formulation is that it actually allows us to directly parameterize or estimate Q value, or the value of executing this entire action chunk for temporally extended value. And this will actually allow us to do multi-step TD backup very conveniently with nice theoretical properties, which I will talk about in a bit. So, okay, how does this work in practice? Our first attempt was actually not that successful. Just a spoiler alert. So what we did was just use this, apply this idea of using action chunk to do RL, and we naively just apply that to, because it's a very simple idea, right? We just naively apply to an online RL algorithm. So RLPD is a very, very strong online RL algorithm. The idea is very simple. It basically just runs stack, or like a TD-based RL algorithm on both like some prior offline data and your online replay buffer. And it just do online RL update on those like off policy data. And if we use this action chunk idea, we learn the same, we train the same agent on action chunk size of 5. We actually see a big performance drop on a lot of environments or a lot of tasks we test on, especially on this like cube task. We do see that a little bit on the quadruple environment, like the very hard environment. We do see that it can sometimes outperform the naive, the online RL method. But in general, it seems to have a very bad failure case. So what is going on here? And we found out that what is missing from this naive online RL methods is that they actually don't have a good expressive policy. And the recipe that we found actually makes action chunking with RL working is that we really need the policy to be expressive, and at the same time, we need to have a behavior cloning regularization on top of the policy. So why is that? So behavior regularization really reduces the action search space. So the action chunking really kind of like blows up the number of action dimensions, right? And if we naively do online RL, we're basically saying that now search for the effect 5 times more like bigger action space, and try to find good action sequence that can lead to good performance, right? It really makes the RL problem much harder. By using a good behavior regularization, you're essentially saying that I want to stay reasonably close to our offline data that already have a lot of sequence of actions that are kind of like temporally, that are kind of like staying, like executing the trajectory and temporally coherent. And this is a connect to the second point where we can actually extract temporally coherent behavior in the data set that can actually help you to explore better in the environment. Right. So if we simply have behavior regularization without expressivity, it will not be able to capture those temporally coherent behavior, because those behaviors requires a more expressive policy to really capture. And the nice thing is that we have already seen these two components before, and we can simply just use our previous work at Qiyang to actually do Q chunking or action chunking RL by simply applying this to the action chunk, the chunking to the policy and the critic. And in fact, we show in our paper that there are other existing offline RL method that we can also use that can also lead to very good performance. And in fact, conceptually, as long as the algorithm contains expressive policy and behavior regularization, in theory, it should really work with Q chunking. This is Q chunking recipe.
Yeah,
So
talking
let's see
about
how.
the behavior. Yeah, talking about the behavior regularization. So, are these offline data always the expert demonstrations? It's like, are they always doing the successful or
Yeah.
satisfying actions so that we can do behavior regularization on top of that? So if they are doing nonsense actions, yeah, just a question. So are these offline samples always successful or always expert ones? Yes.
Right, great question. So for the OG bench task, the trajectories are usually play style data set, which means that it is for the cubes, it's basically grasping a cube and put it into some sort of like a random position or something. So it's really not expert data. But the behavior regularization really gives you a good prior so that we know the grasping behavior is like sort of like a one thing together, right? This is where why like action chunking is really helpful because we no longer exploring the space by randomly jittering in the action space, where by following the behavior policy or the behavior data distribution, we're sort of like saying that, okay, these are the sensible temporally coherent action that we should really follow. And by using these kind of actions, we can actually get a good exploration strategy, which we will see in
Yeah,
a bit.
I see.
Thank you. Okay, so a little bit of results with Q chunking. Well, really, we're just applying action chunking on top of FQL. We can see that we can get really, really good performance on these manipulation tasks, which contains offline data with normal covariant behavior. And by like really capturing those temporally coherent actions, we are able to get really, really good online sample efficiency. So just to interpret the results a little bit, the first half of uh, the graph is the offline training, and the second half is the online training. Right. And something to know specifically is like on this cube quadruple task, which is the most challenging task that involves manipulating 4 cubes. We're able to get much better success rate compared to any baseline. And the only more successful ones are the kind of the RL, the one with action chunking. And we will see more comprehensive results in a bit. So as I mentioned before, this Q chunking recipe should also apply to other methods. And we actually found a really, really simple method that, to our surprise, works super well, which I'm excited to present here. Essentially, this method is really just about training a behavior policy and then sample from it. So what does this RL algorithm do? How does this RL algorithm work? Essentially, it pre-trains a behavior cloning policy on the offline data, and it uses best of n sampling for policy extraction. So what does this mean? We basically sample n actions from the behavior policy, and we use the current Q function to determine which action we should really output from our policy. We just take the argmax of these these n actions by ranking the critic or the value of these actions. And the critic learning, we're basically doing the same thing, the same BOM backup, TD backup, where the Q target is computed using the same behavior or the policy extraction method as well. And for those of you that are familiar with RL literature, you might have noticed that this is essentially Emac, which is expected max Q operator. But we use the behavior policy as the flow policy. Oh yeah, so the BC policy here is we train it with the flow policy, which is expressive policy. So how does Q chunking work? We essentially do the same thing, but now on the action chunks. So a little bit different. The behavior policy now predicts action chunks instead of just one action, and we're selecting best of n action chunks using the critic function, and we're doing this TD backup in with the n-step return instead. So we already seen that QC or Q chunking on IPL works super well. Now, this very simple method without any distillation, just be running the behavior policy and do best of n or sample and rank, it can also work super well and sometimes even outperform the FQL method as well. So as I mentioned, the behavior cloning term really gives you a way to kind of extract the temporally coherent behavior from the prior data. And this is exactly what we're seeing in practice. So we visualize kind of the trajectory of the Q chunking learning process and the one without Q chunking. And we see that, well, it's not like able to success 100%. Its exploration trace exhibits this behavior that is very temporally coherent. And without Q chunking, it can often get stuck when it was trying to explore because it didn't have the sense of like temporal coherency in its policy. And we can even quantify this by measuring sort of the distance that the n effector travels in 5 steps, where 5 is the action chunk here. And we see that the Q chunking method actually have a larger distance that the n effector or the n effector, which is kind of the gripper position, how much the n effector travels in 5 steps compared to the baseline method, which is not use action chunking. So I mentioned previously that there was a side benefit of using action chunking with the policy and the critic. And this is part of it is because we can actually do n-step return backup, but in a way that is unbiased, which I will explain why that's the case. So for those of you that are not familiar with TD learning, how TD learning works is essentially that we're trying to back up our current value or the value of the current state and action as a summation of the current reward that you're receiving at the current time step, as well as the future or the next step Q value if you follow the same policy. So here it's basically gamma, which is a discount factor that people usually use so that your value is bounded. Usually the gamma is like below 1. But essentially it's summing of the current reward with a future value as like a dynamic, approximate dynamic programming. And in practice, this can be slow because imagine each learning process is only trying to back up the value in the next step to the current step, right? So imagine you have 1,000 step trajectory. It will take basically 1,000 gradient steps to even propagate the signal back from the end to the beginning. So this is why a lot of people in the past for dealing with long horizon tasks have used the n-step return, which is nothing but basically saying that instead of backing up the value from the immediate next state or the next state in the trajectory, we're going to back up the state h step or n step into the future. Right. And this is done by adding up all the reward you're going to get in the same trajectory, as well as the value that you predict to have in the future, right? But the problem is, if we do this for TD backup, the reward you're getting along the trajectory is actually not following your current policy. Because the reward you're getting is essentially the reward that you have in your off-policy data set, which is collected by your either like an exploratory policy in the offline data or in your replay buffer. It's an older version of your policy. Right? So technically, the Q or the value estimate is biased in a pessimistic way. That goes more closer to the behavior policy. So something nice about Q chunking is that because we are not modeling just the current action, the value of the current action, we're modeling the entire action chunk, the state and the entire action chunk. Now the same quantity here actually becomes unbiased because it's essentially the same reward that you will get if you carry out this exact same action chunk. So the Q value here actually follows the behavior, the Q value of your current action chunk policy, different from the n-step return case. So this is why the n-step return backup in Q chunking is unbiased. So the first thing that I want to show here is that the n-step return actually allows faster value convergence. As I mentioned before, it backs up the value n-step into the future. You can see this by looking at sort of the convergence rate of the Q value here. So we plotted the Q chunking, which is in pink, and the n-step return baseline, which is in purple, and FQL, which is the last one in blue. You can see that both of the n-step return methods is able to converge much faster than the non-n-step return method. But this does not, like, just having n-step return does not translate to very stable learning. And in fact, we can see in some cases, just using the n-step return with the biased estimate can lead to unstable learning online. And this is in one of the hardest environment that we have seen. Right. So, okay, let me just finish this up. So how does Q chunking or QC compare to prior offline to online RL method? So we see that over all the 5 OG bench domain, we tested offline to online RL. We see that it sort of performs very well over the board, especially on Q quadruple. It's able to do super well online, despite not having any offline success rate. This really highlights that this Q chunking method really gives a very nice way to do effective exploration by sort of like capturing the temporally coherent behavior from the offline data. And compared to naive n-step method, as we showed like one of the failure example, but for in aggregation, we can see that it's not able to do super well, and oftentimes underperforms the one that without using the n-step return in our benchmark. So finally, how sensitive is Q chunking to hyperparameters? In our experiment, we actually use critic ensemble. So usually in TD learning, we have a critic ensemble size. Actually, we found that if we just increase the number of critics in the ensemble, we can get a much better performance. So this might mean that the result can be much more stronger if we have if we're willing to spend more compute on like doing RL training. And another very interesting thing about the action chunk size is that we can actually get slightly better performance by using a larger chunk size. So in our paper, we use a chunk size of 5, which is shown here. I don't know if you guys can see my cursor actually. Okay, great.
Yes.
Yeah, so the chunk size 5 is over here. And you can see that if we increase the chunk size to 10, it can actually do a little bit better as well. So I believe this is on one of the cube triple tasks, which is one of the tasks where you can really see differentiation methods, not like the quadruple task where it's either like success or completely fail. So we really see that there's like kind of like a differentiation in how a larger chunk size can even improve the performance more. But for just computational efficiency, we just use 5 in our experiments. And this sort of plateaus a little bit at 25. And I believe if you run this with a larger chunk size, which is not shown here, with like 40, it will completely fail again. Because at that level, you're really now giving a lot of chance for our algorithm to really stitch trajectories, because you're effectively operating in like a much longer horizon, assuming that you cannot stitch between within the 40 steps that you're considering. And finally, we also try to do UTD or update to ratio ablation. And we found out that if we increase the number of updates per environment steps, it doesn't really improve the performance, which could mean that, well, our method could be bottlenecked by the number of environments. But what I really believe in here is that there are probably better ways to further improve our method so that it can be much more sample efficient. Because usually in sample efficient RL, you're going to see a lot of benefit by increasing the update to data ratio. Okay, in summary, Q chunking, we really address this question of how to leverage expressive policy to explore online. And the answer, the one-line answer I'm going to give is like just apply action chunking to both policy and critic, and use an expressive policy with a behavior constraint to stay close to the offline data. And that is how you can really get expressive or effective online exploration with good sample efficiency. Yeah, I think that's all I have. And big thanks to my collaborators, Sohong, Paul, and Sergey. And we have open source both the code for both projects, and you can find, I guess I provide a quick link here, but you can also find it on our website as well. Yeah, thanks for listening. I will take any questions.